All right, recording is rolling. Welcome to Friday, November 3rd. So, you guys' puzzles are due today. Trying to send to the grade trade. We're talking about chapter 10, 11. Right, been doing these last few days. Right, so, trying to send the grade tray, and I will get those checked off and points in the grade books. Guys, what's due on Monday? Energy quiz. Oh, yeah. So, Monday, you bring energy quiz. Grade that too. And then Monday, we're going to start on momentum, which is all those posters over there with the blue banners, which I did already print out for you guys and give you guys the thumbnail version of this. Right? And so I got some demos for you guys today. Demo on Power Derby car, which I think I may have mentioned last couple weeks. So we'll watch a little bit of that. Okay. Hydraulic jump, which is pretty interesting. And then I got TED Talk for you guys. You guys have a quarter page with actually got a couple TED Talks lined up. So depending on how time plays out, right, you guys got a quarter page in front of you. All right, so let's switch over here and check out what's going on with, first of all, it's Pinewood Derby. Right. Did you guys know channel, this guy's Mark Rober, has a YouTube channel. Do you guys know his channel, maybe? He used to be an engineer for NASA, and now he does a bunch of science stuff on YouTube. And this one's going to meet this guy and narrate a little bit. So get this block of wood out of this box. You guys see about how big it is, and you guys see the racetrack, right? So you let 2 or 3 cars go down at a time. Boom, there they go, and then somebody's going to win. So what's the tricks for making this car work? So it goes through. There's a whole long video. I'm going to skip to different sections of it. He shows physics principles, which it's like mostly conservation of energy. It's like most of the explanation for this video. And then he'll do empirical testing. Like one of the things he says is like, where should you put the weight in the car? Let's get past this a little bit. Right. Blah, blah, blah. Right. Like if you put the weight near the front versus there it is. Okay. Right. Near the front versus near the back. Right. So right here. What would be better for like a faster car? Well, now this is kind of a cartoonized version of the track, right? There's a height drop, and then there's kind of at some point it levels out. Now it's more realistically, it's more of a gradual change, but this works for this explanation, right? So if you put the weight near the front, like this blue car, then when the blue car gets to the bottom, okay, well it's done speeding up. Versus this red car, if the weight's kind of near the back, isn't it kind of like it still has some height to fall? Like it has more gravitational potential energy, which means by the time that these 2 cars get to the level part of the track, okay, yeah, there you go. Right, the red car will have had more potential energy, so now has more kinetic energy, right? So more, right? So that red car is going to win the race, right? Now, if you go and do the empirical science, there's some optimal place to put the weight. It's not the exact back, but it's definitely like closer to the back than the front, right? So that's one way to win. And then, okay, he goes through a bunch of little things, but let me find. Here it is. All right. Right. He sets up a conservation of energy equation, and he does this with blocks. I like the blocks. I think it's a good visual. Right. So it all starts with gravitational potential energy. That's the blue box. Right. Oh, look, weight times height. In the class, we've been calling it MGH, right? MG times H, MGH, right? So there's like the source of energy. Right. Got some car sitting on the top. Again, if you put the weight closer to the back of the car, it'll give it a little bit more potential energy. Right. So that's going to turn into well, there's different places the energy goes. You want it as much of it to go into this linear kinetic energy as possible, because that would give the car greater speed and it's going to win the race, right? The faster it goes, right? And so how can you do that? Well, there's going to be some frictional loss. Now, the way we've been setting up an equation in this class last couple of weeks is to treat this as an open system. I might say the blue minus the red equals, and then whatever you have left over. He has a little bit of a different setup, but it's the same idea. It gets to the same solution, right? It says we start with this blue potential energy goes to 3 different places. One place it goes to friction. Those red blocks represent friction, right? There's a little bit of friction loss, right? You want to minimize that, obviously, right? So that you can get more energy to go into like its motion. But there's 2 types of motion going on: the green and the yellow. Right? So what is green? What is yellow? Green is the translational kinetic energy. There's your 1/2 mv squared, right? Some do with like the motion of the car, put a radar gun on it, the V, the whole deal, right? That yellow blocks is rotational kinetic, which I've mentioned a little bit in here, but in December we're going to come back and do more. So that's like the energy that into making the wheels rotate. And there's 4 wheels. So something to do with like 1/2 I omega squared of the wheels rotating, something like that. Again, in December we'll come back and talk about this more. What if you have like a ball rolling down an incline, right? That's kinetic, but it's like kinetic. It has to do with like rotational. And one of the biggest tricks he gives in this whole video to winning this race is to actually bend one of the wheels off its axis. So the car doesn't actually ride on 4 wheels, it actually rides only on 3 wheels, so that one wheel isn't even rotating at all. And the advantage of doing that is that that's energy that's not going into making that 4th wheel rotate, which means it's left over to go into its translational kinetic energy. So those cars always win the race, right? The cars that are only going on 3 wheels, right? Those win the races. All right, there you go. All right, another demo I have lined up for you guys is hydraulic jump. Let me start with the ones that aren't like as good, but you see them like out in nature. Back when I was in college, I took 2 classes on water and the motion of water. One was called hydrodynamics, and the follow-up was called hydraulics. Those are 2 of the hardest classes I took in college. And it's basically like, how does water flow? How do you get flow through the films? In this case, we're like a storm train. What's going to make water do what it does, right? And really, the backbone of those classes starts with energy and conservation of energy. The water version of it is called Bernoulli principle. We'll talk about next semester. It's basically conservation of energy, just put in pressure units instead of energy units, but same principle, right? But then you can build on that. You can get more complicated. So, well, what if you have like these drag losses? What if water goes around a corner? Or right? You can get to these really weird scenarios. In this case, you guys see the water like flowing uphill. It looks like it's like flowing uphill, doesn't it? Is my screen frozen? Okay, hold on. I gotta pause this video. All right, pause. All right, recording is resumed. I think I got us back here, got us reconnected. Right. So this one kind of hard to tell, but you're like looking down on some kind of storm drain. And I couldn't tell you all the details because this class took a long time ago. It was pretty tough. But somebody like the electrostatic properties of water, and if it's in a channel, it's so deep, it gets going so fast. You constantly get, in this case, the water looks like it's flowing uphill. So I'll show you guys the laboratory version of it. Right, so this is like the really clean version of it, right? Okay, so I got a bunch of students in the lab. Let's get this water flowing. Okay, so we've got water, some kind of properties down at the molecular level. There's a channel so wide, so deep, so fast, and boom, it's up this hydraulic jump. Right at the hand, right place here. Right, and pause it right there. Right, there's a good pause point. So you guys see the shallow water leading into this deep water, right? It's not something you normally expect to see, right? Like things tend to go downhill, balls roll downhill, water flows downhill. It tends to go from like high elevation to low elevation, pick up kinetic energy. This looks kind of backwards, right? But if you get the conditions just right. So there's a bunch of kinetic energy on the left, a bunch of 1/2 mv squared. And there's a little bit of kinetic on the right, but a lot more potential, a lot more MGH. Right? Now, if you do energy accounting, I'm saying like 1/2 mv squared versus MGH. Now, in terms of water, you could do a continuous flow rate and do in terms of pressure, and but the framework we've been using, conservation of energy, can get you started, right? There would be a mechanical energy loss in this turbulence right here. Here's your hydraulic jump, right? This turbulence, right? Now, that energy doesn't disappear from the universe. I bet a lot of it turns into thermal energy. So if you put a thermometer in the shallow end here versus put a thermometer in the deep end, I bet the water heats up a little bit going across this hydraulic jump, right? So there's an energy transfer here, right? Anyway, that's a fun one to solve. All right. Last thing today is I got a couple of TED Talks lined up. Wait, where's the, all right. So you guys got a chord page in front of you?